the physical forces that we haven't talked about. Okay. We are going to take a tour of the periodic table. We've already introduced some aspects of it. And we'll talk about the properties of the elements, and then if we have time, we will get to talk about moles, okay? All right, so again, so we've been talking about isotopes and average atomic mass, and we did a few sample calculations, but let's start again reviewing what we've already learned by looking at these two questions that were in the slides. And in this case, okay, we're going to be doing some calculation and some just reasoning it out, okay? So sometimes you don't have to do a full-fledged calculation to figure something out, okay? So we've got indium. It has two stable isotopes, okay? One of those isotopes has an atomic mass of 112, and then the other has an atomic mass of approximately 115 atomic mass units, okay? All right, and I haven't told you anything about the abundance of those, but we're telling you that the mass, okay, of indium, the average atomic mass, so this is the thing that we've been calculating, right? Is 114.82, okay? So, without knowing abundances, without doing any calculations, we can figure out which one of these isotopes is likely the more abundant one, okay? So, if the two had the same abundance, right? So we've got 113 and 115, right? Rounding, okay? If they were 50-50, okay, the average atomic mass would be right in the middle, right? So the average atomic mass would be about 114. But the average atomic mass, we've been told, is 114.8, okay? So which of those two isotope masses is that number closer to? Is it directly in the middle of these two, or is it closer to one of the two isotope masses than the other? Yeah. Yeah, so this average atomic mass is closer to the mass of indium-115 instead of indium-113. Okay, so it's not directly in the middle, it's closer to one than the other. Okay, so what does that mean in terms of which of these two is more abundant? Yeah. 115, right, because if it's more abundant, okay, then its fractional abundance is going to be a bigger number, and the average atomic mass that we calculate is going to wind up closer to the number of the more abundant element, okay? So, in this case, okay, the thing that we can say is that indium-115 has the highest percent natural abundance because the average is closest to that number, okay? So, we can rule out the ones that have indium-113 either as abundant or more abundant. And then, why can we rule out the second choice? Most indium atoms have an atomic mass of 114.82. Why do we know immediately that that can't be true? Bless you. What type of number is 114.82? in mathematical terms? Is it an integer or a real number? It's a real number. And remember, an individual atom, the mass in atomic mass units is the sum of the number of protons and the number of neutrons it has. So it's always going to be an integer, okay? So this isn't an integer, okay? So that mass can only represent the average mass of a group of atoms, not a single atom, okay? Percent mass of a group of atoms, not a single atom. All right, so we've got another element that has two stable isotopes, okay? The first one has a mass of 68.9 and an abundance of 60.4%. Okay, what's that going to be in terms of our fractional abundance? What number am I going to wind up putting into my formula? So remember to go from percentages to fractional abundance. We're going to divide by 100. Okay, so 60.4 parts out of 100 parts gives us 0.604. Okay, so our second one has a mass of 70.9 and an abundance of 39.6. So that's 0.396. Okay, so the atomic weight, the average atomic mass of the element, is going to be 0.604 times 68.9 AMU plus 0.396 times 70.9 AMU. So numerically, let's see what that winds up being. So we got 0.604 times 68.9 plus 0.396 times 70.9 parentheses. And so we get 69.69, so 69.7 atomic mass units. So a couple questions we want to ask ourselves is, does this number make sense? Okay, so we had two isotopes, one of which was, almost twice as abundant as the other. Okay, so our average atomic mass we would expect to be closer to 68.9 than 70.9. Okay, and so we do wind up. It does wind up closer to that. So that's thing number one. Okay. Thing number two is remember that our fractional abundances, those two fractions, or 3 or 5 if we have 5 isotopes, those numbers should add up to 1. Okay? The fractions should all add up to a whole. Okay, so you can imagine that the abundance of each isotope is a piece of a pie, and that all of the isotopes that that are considered in our average atomic mass or that exist have to equal one whole pie. Okay, so let's just do a check on that. Okay, so we have 0.604 plus 0.396, and those do in fact add up to 1. Okay, so they add up to 100% of the material that you find, if you were to take samples of this element. All right. Okay, so just quickly looking at, at the natural abundance of isotopes. So this is a table that shows, the abundances as little pies arranged on the periodic table. So here what you can see is if we look at fluorine, there's really only one isotope of fluorine that we ever see, okay? And so if you look at the average atomic mass, 18.988, there is almost undetectable amounts of any other isotopes of fluorine, okay? Whereas if we look at some of these elements in the middle of the periodic table, okay, you will see that their pie charts have lots of different color slices. There's lots of different isotopes of these elements, okay? And again, this is if you take a sample of that material and you analyze, all the atoms in it, what are the masses, how many neutrons does each sample, does each atom in that sample have? So the other thing that you might notice is that there are a lot of elements, okay, that have white circles. All right, so many of these elements, okay, are not found significantly in nature. They've only been created in the lab, okay, and so they don't actually have any stable isotopes. Okay, so we're going to talk about where that hits on the periodic table. Okay, but you'll notice that the key kind of point in the periodic table where things start to go is right here. Once you get above an atomic number of 83, okay? So if we look here, okay, all of these elements here, their atomic numbers are above 83. This promethium is the kind of one exception, okay? Atomic numbers above 83 have no stable isotopes. So let's talk about what makes isotopes stable, okay? All right. So I'll come back to how we use. I'm going to rearrange my slides a little bit. So we're going to talk first about stability, okay? And then we'll talk about how we use isotopes, practically speaking, okay? All right, so to this point, okay, we've talked about some forces, okay? So things that are going to draw particles towards one another or away from each other. Okay, so the one force that we kind of all experience, right, is gravity. It's why we're not floating around, okay? And gravity has to do with the mass of objects. So when we're talking about subatomic particles in the nucleus, their masses are so tiny that gravity doesn't really play a huge role, okay? So gravity is related to mass, okay? And it's also a very weak force. So you have to have a huge mass to get a fairly weak force. Think about it. The mass of the Earth is what is holding us onto it, right? And so you have to have, something that's really huge to have significant gravitational attraction. Okay. So the other force that we've talked about so far is electromagnetism. So we talked about Coulomb's law. We talked about how charges of opposite sign attract one another, charges of the same sign repel one another, okay? And that the distance between those objects is going to affect how strongly that attraction or repulsion pulls on them, okay? So we're going to talk about how how the force of electromagnetism plays a role in nuclear stability, but also two other forces, okay, that are what are responsible for nuclei being stable or unstable, okay? So why we might have, okay, isotopes, you know, that we see and that we can analyze when we take up samples of elements, and why there are other elements where their nuclei aren't stable and these things decay, okay? And that's what radioactivity is. It's when nuclei decay and they break down into something else, okay? All right. So we have a interplay between things that are going to hold the nucleus together and things that are going to tend to make it less stable or push the particles in the nucleus apart. Okay? So we have in the nucleus, remember that we have protons, which are positively charged, and neutrons, which have no charge. Okay? So we've got our protons. Just going to draw a couple protons here, and our neutrons, which I will make kind of black and neutral here, okay? Not very interesting. All right, so if I'm talking about the force we know so far, electromagnetism, okay? The nucleus should not be stable, right? Because the protons should be repelling one another, right? Because they're all positively charged. We try to cram them into this closed space. They're going to tend to push each other apart, okay? So that's going to be a destabilizing force. So electrostatic repulsion of protons is something that would make the nucleus less stable. So that cannot explain why all the protons are found in this tiny little area, okay? So there are two other forces. One is called the strong nuclear force, and the other is called the weak nuclear force, okay? So our other two forces, okay, called the strong nuclear force and the weak nuclear force. So the thing that actually is the most responsible, okay, for a nucleus being a stable entity, having a bunch of positive charges right next to one another, okay, is this thing called the strong nuclear force. So the strong nuclear force is 100 times stronger than the electromagnetic force. So as a force, it is much, 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 much stronger. Okay, so that's kind of the first thing. Okay, so the strong nuclear force is 100 times stronger than electromagnetism. All right, and I've posted some links to videos in the chapter 2 kind of extra stuff area. And one of them is from this guy, Dr. Doug, from Fermilab, which is, it's a huge national lab that studies subatomic particles, okay? And they do very sophisticated physics. But he does a good job giving an example of, you know, how much force, okay, do two protons in the nucleus actually exert on one another? Okay, so if you went and calculated it out, you know, scaling for size, okay, the protons in the nucleus would be repelling each other by, I think he said something like 70 or 80 pounds of force. And given the fact that these particles are so tiny, imagine, you know, if you put that much force on them, they would go pshoo, flying, okay? But when you have an attractive force, okay, that is 100 times stronger than that, okay, you can counteract that and keep things together, right? So it's, if you ever watch like a disaster movie where there's, flood or something and they've got a door and they're trying to keep it closed, right? It's whether that door gets open or closed and the chamber floods or not is, can they put enough force on that door that is stronger than the force of the water trying to push it open, right? So, in the case of the nucleus, okay, are the forces attracting the protons, okay, going to be stronger than the forces pushing them apart. So the strong nuclear force is much, much stronger, okay, than electromagnetism. Okay, it attracts protons to one another. So that's great, okay? If that's true and that's the only thing going on, okay, why do we have things like radioactivity and unstable nuclei? Okay, if the strong nuclear force is so strong, why would we ever have an unstable nucleus? Okay? And the catch is that the strong nuclear force requires contact between the particles that it's attracting. Okay? So it's very, 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 very short range. Okay? Electromagnetism can act over some distances. Okay? The strong nuclear force requires contact. Okay? So the big but, okay, is that it's a very close range force and it requires contact between the particles. All right? Yeah?
If you had more protons, would that mess up the...
So it is all, and there's a figure in your textbook, and I have it in the slides. It's all this balance between how many protons, how many neutrons you have, and so neutrons, as you can imagine, just looking at my little diagram here, okay, neutrons are going to get in the way of protons having contact with one another, right? So the more neutrons you add to your nucleus, okay, the less stable it gets. So what we tend to find is, it's the heavier isotopes that are the less stable. Okay, so if we think about just the isotopes of hydrogen that we talked about, the one that has no neutrons, the one that has one neutron, and the one that has two, okay? The one that actually has radioactivity is tritium, the one with the two neutrons, okay? Now, that's a bad example. Why is that a bad example, Dr. Gallagher? How many protons does hydrogen have in the nucleus? Yeah. It's only got one, so there's no magnetic repulsion or whatever. But if I had picked a better element, what we'd find is that the heavier isotopes are going to be the ones that tend to be less stable, because again, the more neutrons you pack in the nucleus, okay, the more crowded things get, the harder it is for those protons to have contact. Okay, and so if they have less contact, the effect that stabilizing effect of that strong nuclear force gets weaker because there are fewer of those contacts, and eventually electromagnetism, electrostatic repulsion is going to win out. Okay? All right. Okay, so if we look, and I'm going to go and show you this slide here. Okay, so what this figure shows you, again, is it shows you the number of protons versus the number of neutrons for different elements. The dots that are in black are stable. Okay, so the title of this figure is The Band of Stability. Okay, so these are isotopes that we see. Okay, remember again our cutoff point. Okay, is that 83 protons. So greater than 83 protons, your element's nucleus is not stable. If we look, again at the things that are in black are the stable nuclei, and the dots that are in red, okay, are the unstable nuclei. So there is a kind of magic ratio, not magic, but there is a specific ratio of protons to neutrons, okay, that creates a stable nucleus. Okay, so things that have even numbers of neutrons tend to be more stable than even atomic numbers, even number of protons tend to be more stable than those with odd numbers of protons. Okay, and again, everything's going to come down to, can the strong nuclear force win out? Okay. So to this point, I haven't said anything about the weak nuclear force. So let's go back. Okay. And all right. So number of neutrons versus number of protons. So even numbers of protons, elements tend to be more stable than those with odd. Numbers of protons. Okay. More neutrons tend to reduce stability of the nucleus. Okay. And again, I'm going to say by interfering with the strong nuclear force. Okay. All right. So strong nuclear force, that's the thing that controls stability. Okay. The weak nuclear force, okay, we're going to say kind of two things about it. Okay. So the weak nuclear force is a force that has that plays a role in the nucleus, okay? But it has little to do with overall stability, okay? It's called weak not because it's weak, okay? So if we were talking about which is the strongest force, so if we go from strongest to weakest, it would be the strong nuclear force, the weak nuclear force, electromagnetism, and then gravity, okay? So if we were talking about our forces of nature, that's how we'd rank them, okay? The weak nuclear force is called the weak nuclear force because it is very, 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 very rare that this force is seen playing a role in nuclei. And the role it plays is when you have an unstable nucleus, okay? When that balance between electromagnetism and the strong nuclear force is off, okay? The weak nuclear force plays a role in determining how that isotope is going to decay, okay? So the weak nuclear force, it's very rare, and it plays a role in the type of decay, okay? So when I say decay, okay, in your head, again, think of the nucleus changing in some way, but the word that may be more familiar to you, okay, is radioactivity, okay? So decay, okay, think radioactivity. And, anybody who has had, any experience with certain types of medical testing can tell you that not all radioactivity has the same level of harm to it, okay? So the radioactivity that one would be exposed to if one were getting cancer treatment, okay, that's going to be high energy, high level activity, radioactivity that's going to actually damage tissues. And that's the whole point. The idea is to kill a tumor, okay? Whereas in some types of medical testing, okay, you have to, drink a cocktail of a radio-labeled substance that is where the material that's in, that your little cocktail that you take before you have your CAT scan, okay? Yes, it is radioactive, but the type of energy that it emits is lower energy and is not going to damage your tissues, okay? So there's different types of radiation. Yeah?
That would be alpha, beta, and gamma radiation, correct?
Yep. So we classify them, by their energies, and we call them alpha, beta, and gamma, okay? And gamma radiation is the highest level of radiation. It's going to do the most damage, okay? Then beta, and then, and then alpha, okay? So not all radioactivity is the same strength or can do the same amount of damage. So whether an element is going to decay by emitting alpha radiation, emitting beta particles, emitting gamma radiation, the weak nuclear force, okay, and how it plays a role in the nucleus is the thing that can cause something to emit beta radiation as opposed to gamma, okay? All right. So that's our discussion of nuclear stability and physical forces. So just another word about isotopes, okay? So, did you have a question? Or no, okay. You're just waving at me. All right, so, so we can use our knowledge of isotopes to do a lot of really useful things. Okay, so if you're looking for some weekend reading or some bathroom reading or whatever, post it on Brightspace. There's 2 articles. One has to do with how we use isotope fingering or fingerprinting or isotope labeling to detect counterfeit pharmaceuticals and to detect doping in sports. Okay, so every material, okay, on Earth, okay, I showed you those pie charts. We've got this mixture of isotopes, okay, and the places that an element is found and the sources and what happens to that element, how it's processed, okay, can affect that isotope ratio, okay? So, and also, the age of the material and things like that. That's how we can do things like carbon dating, okay? So, the ratio of different isotopes in a material can tell us where it came from and what happened to it, okay? So, excuse me. So, if I am... There are even plants have preferences for materials with certain isotopes over another. Okay, so we can tell if a drug was freshly made over in Hobart at Mallinckrodt, okay, or if that drug actually went through someone's digestive system and was excreted in their urine, kind of thing. So, and the way we do this, okay, is we do something called isotopic analysis. The technique we use is mass spectrometry, okay? So mass spectrometry hits molecules with enough energy that it causes them to ionize. It knocks electrons off of them, okay? And what it then does is it's looking at kind of the behavior of the nuclei, and it puts it in this kind of chamber that may have, there's different types of techniques, okay? So it basically measures how the material kind of flies, and if it's heavier, if it's got more neutrons in it, it's gonna kind of fall faster. If it's lighter and has less neutrons, it's gonna fly differently through this chamber. Okay, so So we can get what are essentially fingerprints, okay, of compounds, okay, and tell something about where they came from, okay. So it's become a really important technique for detecting fraud in pharmaceutical manufacturing or food manufacturing, and this can be a real problem, both as a danger to the consumer who's consuming that product, okay, if it's adulterated with some type of harmful material, okay. We can fingerprint the active ingredient, find out where that came from, and then know where in the world to look for the entity that is spiking the food or the drug with something dangerous, okay? We can use it, again, in sports instances. We can tell if somebody, if a hormone that is found in the urine of an individual is something that was produced naturally by their body or was, introduced through doping, okay? And all because there will be different isotope ratios in the atoms that make up those molecules, okay? So there's lots of different things that we can do that are interesting with isotopes, okay? All right, we're gonna skip binding energy, all right? We talked about, again, even versus odd number of nucleons, number of particles. And again, you can kind of look and see patterns, okay, that arise in terms of the isotopes. All right. All right, so now we're going to start our tour of the periodic table, okay? And we are going to use, the standard version of the periodic table, okay, that is, boring and organized in squares and rectangles. But there are lots of chemists who have arranged the elements in the creative ways, some of which you see up on the board, that arrange the elements according to different types of properties or arrange them in such a way to highlight a property that's important to the designer of the periodic table. All right, so here's the modern periodic table. Take yours out so you can make notes on it if you want. Okay. So we've already talked about how to interpret one of the boxes, one of the squares on the periodic table. So now we've done the kind of the zoomed in view. Now we're going to do the zoomed out view and talk about the structure of the periodic table, okay, and what the position on this table tells us about a material, okay. So the periodic table was originally organized, okay, by physical property. Before we had the modern atomic model, before we knew about protons, neutrons, and electrons, okay, people were trying to organize what they knew about materials so that they could try to figure out what those materials were actually made of, okay? And so the way that they were arranged originally, okay, was by their mass and physical properties, okay? So, the notion that matter was made of atoms, okay, was, thousands of years old. We didn't quite know what atoms were yet, but we knew that we could break things down into these little individual blocks called atoms, okay? And so originally materials were arranged based on their mass, okay? And Dmitry Mendeleev, who is the person who established this organizational structure, okay, when he was arranging the elements, okay, we hadn't discovered all of them. We had only discovered, a couple dozen. And some of the ones, okay, that are, were around here, let me see, germanium, that was one of them, okay, hadn't been discovered yet, okay? And what he did was he came up with this system for arranging things. They were based on the masses, the densities, the boiling points, the melting points, other properties, okay? And, and what he found was, the materials on either side of where germanium is, okay? If he put arsenic over here, it kind of broke the pattern. So he said, well, you know what? I'm going to leave a blank there in my periodic table, and I am predicting that there's a material that has the properties that will put it right in that square. Okay? And so that's one of the reasons why his version of things, his arrangement of the elements, became the one that most chemists adopted, because he was able to predict the existence of materials that hadn't been discovered yet. Okay? So as we learned more and more about the elements, okay, what happened was arranging things based on their mass alone led to some inconsistencies. And once we discovered what protons were, okay, there's a scientist named Morley who said, you know what, let's change our organizational principle and say we're going to organize the elements by increasing atomic number, increasing number of protons in the nucleus. Okay, and so it pretty much correlates with mass, but that's the principle that we use today to organize the elements. Okay, so all right, so what you'll notice, okay, is there is this feature right here, okay, the red arrow, and if you look closely at this portion of the periodic table, you'll notice that we go from element 57, lanthanum, to hafnium, 72. Okay. And so we're kind of 1, 2, skip a few, right? And here's what happened. You'll notice that all those numbers that should be in there go here, okay? And the sole reason that these groups, okay, are taken out of the middle of the periodic table, okay, is because we want it to fit neatly on a piece of paper so that we can read it. So this is what the periodic table would look like if all those elements were just, laid side by side. We'd have this really wide periodic table, okay? So the rules, again, for these elements here in terms of, in terms of periodic table organization, they still apply. This is just more of a fitted on one page kind of choice. Okay, so these materials right here are given special names. Those two rows. The first one is called the lanthanides. Okay. And it's because it's the elements that come after lanthanum. These guys are called the actinides because they're the ones that come after actinium. Okay, and so that's why those are named the way they are. All right. So let's talk about groups and periods. Okay, so we give different names to different regions of the periodic table, okay, because they give us different types of information. Okay, so in chapter 3, okay, we are going to talk about electronic structure, okay, and we're going to talk about the fact that electrons, we've already talked about the fact that not all electrons are the same distance from the nucleus, right? So in chapter 3, we're going to talk about the energy of electrons, okay, and how that changes, okay? So the rows in the periodic table, okay, tell us something about how many different steps of energy, how many energy levels there are in our atom, okay? So so the rows are called periods, okay? And the periodic table is called the periodic table because the properties of the materials, okay, vary periodically, regularly, as you go from left to right across the table. Okay? So, periods are the rows, and the properties of elements vary periodically as you go within a period from left to right. And as we go through this course, we'll get more and more specific about what, the ways in which those things vary. Okay. So before we do that, let's talk about the columns. Okay. So the columns of the periodic table, okay, are called groups. Right? And the groups can also be called families. Okay? So these are groups. So the rest of the world, okay, just numbers the columns 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 18. Okay? You will notice in the version of the periodic table that your textbook uses, and the version that's typically used in North America, okay, there's another set of numbers, okay, that have 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and then another set of columns are numbered with B. So we've got 3B, 4B, 5B, 6B, 7B, and so on. Okay. Now, those AB numbers are going to be a quick way for us to determine something about the number of what we call valence electrons in our atom, so the number of reactive electrons in our atom. Okay? So what you'll find is that the columns or the groups, okay, have all of the elements in that column behave chemically in a similar fashion. Okay? Now, we'll talk about that in terms of reactivity and things like that. As you go down or up a group, the kind of magnitude of the effect changes, but the chemical effect of everything in that group is similar. What it reacts with, what it doesn't react with. Okay? So we'll talk about that on Friday. So have a good afternoon. Do not forget to bring goggles and stuff to lab.